Good afternoon, ladies and gentlemen. Thank you for joining us for today for this webinar session on the interesting topic electronic skin from conformal interface to sense digitalization. This event is brought to you by NTU Institute of Advanced Studies, the, the graduate student clubs of Materials Science and Engineering, and the School of Electrical and Electronic Engineering. My name is Harutai, currently a president of GSC MSE, and I will be the host for this webinar with Vijay, president, and Adhesive, vice president of Triple E, as the co-host. Please take note some of house webinar rules. If you would like to ask questions during the Q&A session, please use the Q&A feature at the bottom of your Zoom screen to post your questions in the webinar. This question will be directed to Professor Chen during the Q&A session. For those postgrad students who require the endorsement of attendance, we will appreciate that your name and affiliation is shown, such as Harutai, open parenthesis, MSEPG, close parenthesis, thus helping our admin colleagues to keep track of the attendance. Additionally, at the end of the session, please fill up the feedback form and indicate the need for endorsement. Today's webinar is being organized as a part of Discovery Science Seminars and Interviews initiative. Now, let me introduce the guest of honor for today's webinar, Professor Chen Xiaodong, who is a global highly cited researcher. His research interests include mechanomaterials science, sense digitalization, flexible electronics technology, and cyberhuman interfaces. He has been elected as Fellow of the Academy of Engineering Singapore and a Fellow of Royal Society of Chemistry in UK. Moreover, his research work was recognized by numerous organizations, according multiple prestigious awards and honors. Some recent awards include Singapore NRF Investigatorship and Fellowship, Small Young Innovator Award, Nanyang Researcher Award, Rubiso Young Material Science Investigator Award, Mizzou Chemicals SNIC Industry Award in Materials and Nanochemistry, and Friedrich Wilhelm Bessel Research Award. Currently, he is the President's Chair Professor in Material Science and Engineering, the Director of Innovative Center for Flexible Device IFLEC, and Max Planck NTU Joint Lab for Artificial Sense at NTU, the Deputy Director of Singapore Hybrid Integrated Next Generation Microelectronics Chi Center, and the Principal Scientist at the Institute of Materials Research and Engineering in ISTAR. Without further ado, let's welcome Professor Chen to start the webinar.
Very good morning, everyone. Thanks for kind introduction, and also thanks for the organizers for invitation. I know it's a very hard time for everyone, and then I'm very happy I can still have an opportunity here to share our recent research in flexible electronics related. And what I'm doing today is I try my best. I know in the audience, I come from different discipline. What I do is I try my best to use the layman term to describe what we are doing, and then to tell you our idea, how we want to achieve it. And then the perspective will be in this emerging electronic skin area. And then, of course, during the Q&A session, I will be happy to take any questions you have, and then have more deep discussion at this stage. Okay, for electronic skin, so this is something about it's kind of recently emerging field. And we are in this field about 10 years since I was joining NTU as faculty. My area starting to work on this kind of flexible electronics technology related. And personally, I'm very happy, we really make some progress, but there are more things are coming now. Give me a second. Okay, so for human skin, it's a kind of very well known. So this is something about the largest organ in our human systems. In terms of total area, it's about 2 meters square. And then you can see for this skin, for simply say the skin is very important, one of the most important is the organ systems. And then it functions as the sensation, regulation, and protection. So what's the reason why you have this kind of capability? What's a big area can interact with the severe? Another is important sensor. There are many kind of sensors on skin. For example, temperature sensors, force sensors, even chemical sensors, and so on. So this is something why the skin is so amazing. And then of course this is something inspires faculties or the scientists to see whether we can mimic, get inspiration for this kind of mimic the skin, and also can develop device inspired for the skin. So this is something the reason for electronic skin emerging out. And then starting from skin, people really try to figure out whether they can do this kind of flexible materials, soft as skin. Skin can have stretchability, and also stretchable electrodes, stretchable circuits, because all this can offer capability not in this kind of material science for new material science angle, and also can develop new kind of prototype this kind of electronic device, like an electronic circuit can be stretchable, can be bendable, and this will be very helpful for healthcare monitoring, prosthetics, even for this kind of social robotics. So this is something I would say huge application. So this is something the reason why there's so many tremendous research effort around e-skin directions. So I just keep this slides. I really summarize what are people are key interested in the e-skin area. So basically, I classify them in 4 parts. First part is about in the electro skin, how really have this kind of electrodes or this kind of film have a sensing capability like skin, and also beyond the skin. So first one, we must need the skin like the tactile, and also temperature, and even other kind of now people adding a different kind of chemistry and so on. So this is something about have a sensing capability there. And then of course, in this sense capability, there's a lot of questions people are addressing now: sensitivity, stretchability, conformability, even long-term stability issue. The second challenge is not only in this kind of non-invasive, this kind of device application for this kind of skin-on-skin electrodes, and also people looking for this kind of self-powering. Even now, people emerging to think about how this kind of electrode can be used for implantable, for interface with the neuron and other kind of even for heart-related this kind of stuff. The third important point is not only about tool function. The second one also about this kind of manufacturing capability. You want to make this kind of project works in manufacturing and also at the end deployments, very important. So let's some people start to think about how we can develop this kind of e-skin, have a self-healing capability, hybrid with this kind of traditional CMOS technology, make an ultra thin, even large area. And last one, I would say people even more interested in one, even this kind of capability, how to integrate with the current device and for this kind of healthcare monitoring and for this kind of software applications. So this is something I would say in e-skin have this kind of 4 kind of research direction people are exploring. But what I'm going to do today, I will cover what we are doing in my groups. So my groups basically focus on interface parts, how we can transduce the biological sense into the digital signal. So this is something the idea for us is the skin, e-skin can function compared with the human skin or other kind of materials. So this is something I would say very good platform. In this case, today I will cover 3 parts. First one, I will show you a story, how we fabricate conformal bioelectronic interface. So this is something more of stuff from material science angle. The second one, I will tell people how we digitalize the biological perception and action. The last one, how we use this kind of e-skin to extend human senses. So this is something the 3 topics I'm going to cut today. In each part, I will just briefly tell you maybe 1 or 2 stories, how we do it, and what we expect. Of course, if you want to hear more or read more, you can read our papers. Okay, first one. So in human system, it's very kind of interesting and also amazing. And just take about mechanical properties. You have kind of big scale, various this kind of mechanical properties. The soft, like this kind of brain tissue, is only about kilopascal. A hard like a bone can go to 10 to 6 times kilopascal. So this is something from huge to this kind of broad. Okay, 6 always significant difference. In a way, give our device fabrication a lot of this kind of difficulty, because a lot of cases we want to use one device for all kind of tissue, but it's impossible. So that's why we have to figure out what the molecular properties there. And then sometimes people have no idea what it means. Kilopascal is 10 to 6 times kilopascal. Let's give an idea. The soft like a tofu, okay? The hard like a bone, like this kind of gold. So this is something about two kind of direction. How soft could be, how hard could be, mechanical properties. Right? And then this leading a lot of problem in device fabrication. For example, one case would be mechanical mismatch interface. You can see for device like this kind, typical this kind of Apple Watch, right? I mean, there's still a problem when you can wear on this kind of hands. There's a lot of gap between the device with this kind of epidermis. So this kind of gap will leading this kind of device in terms of the signal noise is very high and very low. And also, because we want this kind of device to be comfortable, it can be attachable or wearable. But unfortunately, for this kind of device, it's easy to peel off. So this is something the problem in this kind of mechanical mismatch. And in terms of signal parts, because our skin have a certain stretchability. For human skin, typically it's about 70% stretchability. But the current device or electrodes, like here, so this is kind of mechanical in clinical use electrodes. All such electrodes, they don't have a stretchability. In this case, you put this kind of electrode on skin. When you stretch it, for this kind of typical electrodes, the skin stretch, but electrode didn't stretch. As a result, the surface electrode potential will change. So this is typical for this kind of traditional electrodes. And then for conformal electrodes, we define here is they will combine the change of skin. So it means stretches skin, electrode also stretch. So in this case, they keep this kind of surface potential stable. And then as a result, if the signal change, we know because of the biological system itself, not because of the system problem. So this is something need for this kind of conformal electrodes. So typically, there are three kind of needs for this kind of conformal electrodes. First one, stretchability, we mentioned just now already. So this is something, make sure you get reliable signals. The second important part is reliable. And then so durable. Reliable, it means the signal gets you can really believe. The third one, durable, is needed for long-term usage. Why you need this one? This is something the figure to share the people. All this kind of electro skin can be used for this kind of muscle activity, for the brain, for the heart, and for even other parts not shown here. So in generally, so this is something about e-skin have a huge impact or have huge impact in healthcare related. But before we reach that part, we need to address three key points: stretchable, reliable, and durable. And for entire stretchable part, of course, how we fabricate. Stretchable electrodes is kind of fabrications more than 10 years already. There are a few kind of leader people in the field, like Professor Zhenan Bao from Stanford. For her group, is interesting on developing this kind of intrinsic materials, like semiconductor polymers or other kind of polymer matrix to make this kind of stretchable electrodes. But this is something called intrinsic properties. The second typical examples come from John Rogers from Northwestern. For his group, he developed this kind of use this kind of silicon base. But what he do is he uses this kind of mechanical design to make this kind of structure can be bendable, foldable, in three-dimensional. When you stretch it, they didn't change the electrical properties of this kind of silicon electrodes. The good point is they really can align or match with current CMOS technology, but with a lot of this kind of additional this kind of methods or this kind of additional modification approach that's problem. And then another two approach is also very often uses pre-strain structure, also crab-based structure. This is used for this kind of stretchable electrodes. Every method has a good point and also have a kind of disadvantage. So this is something when people try to figure out the combined approach to do it. So a few years ago, we also start to think about how we can really make it kind of stretchable and also conformal electrodes. And one of our first system we developed is to combine this kind of structured PDMS with the gold ribbon. And this gold ribbon was transferred to the pre-strain PDMS. So in this case, the PDMS release, the metal will bend. And then in this case, stretch or release, in this kind of release, they still make sure the good connectivity of this kind of gold materials. So let's say, so here, the stretchable can stretchable up to 130% without changing the resistance. The typical gold, less than 10%, they break already. So that's essentially one stretchable electrodes we fabricate a couple of years ago already. But and also we do is this experiment, also do this kind of animal experiment to really tell people this can be used for this kind of healthcare monitoring. But this is not industrial acceptable approach. One reason is a stable issue. So by this way. So because we transfer gold onto PDMS, and the interaction is kind of non-covalent bond. So in this case, you just use a Scotch tape, you can peel off, very easy to peel off. So a similar way for other kind of case also, for our case also, very easy to peel off for electrode from PDMS substrate. In this case, we ask ourselves questions, how we can really address these questions, interface question, make this kind of stretch stable, this kind of composite electrodes. And then when I was a PhD student and handling a lot of FM measurement. So for FM, atomic force microscope. So for FM, there's one very fundamental theory called JKR adhesion theory. You want to have two materials to strong interaction, have a strong adhesion. Either part, you change two materials, but of course, in our gold PDMS case, you cannot change it. But another possibility is you increase contact area. So as shown by these figures. So here's the gold, the PDMS, here's gold. So we peel to come out with this kind of mechanical interlocking model. In this case, you have increase the surface area of these two materials, and also have the friction between two materials. So this is two of the interaction, this kind of two interaction to ensure these two materials are strongly interact together. And then the answer yes, they can. Here we use this kind of AO membrane to fabricate this kind of gold nanorods, and then we're pulling over PDMS there to make the construction. So adhesion strength increased more than 10 times. It means that do increase stability of this kind of two materials. They will not peel off so easily anymore. Therefore, we also publish paper. But again, it's only can use for publication. Why? One of my PhD students, he spent almost 4 to 5 days to fabricate these samples. Okay, it's about maybe about 5 by 5 this kind of sample size in centimeter. And then it's not very efficient. Although in science, we say it works. But this science to us, you want this kind of interlocking structure. The way you do here is very kind of order interlocking structures. The answer is whether we need such order structure. Of course, no need. As long as a random structure, it works, right? Then we go back to the 2D film, this kind of growth. In this case, for gold, by thermal degradation can deposit on this kind of metal or other kind of solid substrate. But if you are material science, you know gold is kind of two-dimensional growth. Gold didn't penetrate into a substrate. So this is the reason it's so easy to peel off, not so stable. Then we question ourselves, if we have idea to make this kind of gold penetrate into a substrate. Of course, this will increase the stability, right? So this is something we turn the science, we do it. But of course, if it's solid substrate, no way the gold will penetrate in. What happened? You put the substrate not in solid state, it's the kind of fluid substrate. What will happen? Yes, if a fluid substrate, it will be penetrated. But of course, in this case, our fluid substrate is not really kind of water-like substrate. It's kind of still look at that part, it's kind of solid substrate, but it's still some monomer or this kind of fluid molecules inside. So here we use the polymer, PDMS. It's well-known materials. For this PDMS, we know already, we can control the time for this kind of curing time. We can control this kind of cost inside. And also, we can control this kind of amount of this kind of polymerization. So this, now of course, how we do it? First one, we use this kind of substrate, it's kind of half cure PDMS. It means still 50% there's some monomer inside. And then we can thermal deposition this kind of metal on top because it's kind of liquid, the gold will penetrate inside. During the thermal evaporation, you have this so-called thermal radiation. So this kind of thermal radiation will further polymerize the remaining PDMS monomer. So in this case, the metal will be encapsulated inside. So this is the idea we developed. So we turn this approach called TRAP, T-R-A-P. Thermal radiation assisted metal encapsulation. So this approach can be used to form highly stable and stretchable conductors. How it works? First one, it's a PDMS, but it's a half-cure PDMS. Still 50% are monomer inside. When you thermal deposit this kind of gold into the substrate, the gold will penetrate, but because the thermal radiation there, the gold will be encapsulated by the PDMS layer. So this is some sort of film we can form. So this is how it looks like. This gold, this is stretchable gold, okay, bendable, and also foldable. The size is really dependent on how large sample you prepare. And then you can see background. The back color is black color. Black color is because gold nanoparticle aggregate there. So that's why it's kind of black color there. Okay, so this is something one kind of electrode we fabricate. Then let's see how this kind of stable here. So here there are 3 samples. This is gold on glass, easy peel off. This is gold on fully cured PDMS, gold also peel off. And this is that use our trap approach to fabricate. You can see, now you want to peel off, the gold is still there. So this is an approach and also conductive. Okay, so this is an approach to fabricate this kind of highly stretchable metal electrodes. And in terms of timing, 2 hours, you can fabricate in very large scale, A4 size. Okay, so this is something of how the surface looks like. Because you can see it's stretchable. Although it's kind of gold color means it makes sure it's conductive. But on surface, still a lot of wrinkle structure. Because this kind of wrinkle structure, like our human skin can be stretched, right? In terms of cross-section area, you can see the 3-layer structure. On surface is gold. In between is gold PDMS. On the bottom substrate is the PDMS. So this kind of 3-layer structure is a very good layer. And then now you know this is something approach you can use for a lot of different kind of application. We very often use this kind of interlocking approach in my group now to fabricate this kind of stable, stretchable electrodes. And then for PDMS, go on PDMS, you can do it. But unfortunately, there are also problems. For this kind of gold PDMS film, it's easy to break. Okay, like a paper. You have an idea of a paper, right? You want to crack there. You just apply a certain force, the crack immediately migrate. Like the PDMS gold film here also. You just apply the crack here, artificially create crack here, 5%, 40% migrate already. It means easy to break. It means the electrode is not stable anymore. So what's the reason here? In material science, you will know this is because of fracture toughness. Fracture toughness is too small. So in this case, we have crack here, the crack will easily migrate with additional stress applied. Now, you want to ensure this crack will not migrate. One possibility is have a larger fracture toughness. Then, how do I do it? So for this work, we work with the number from Stanford, from her group. Her group is very good to develop this kind of quadruple hydrogen bonding, this kind of super molecular polymer. For this super molecular polymers, have one component called UPY. UPY have a quadruple hydrogen bond length, and then ensure this polymer is highly stretchable. It can stretch up to 20 times. What's the reason for this kind of electrode so much stretchable and also self-healing? because they have very large this kind of fracture toughness. This fracture toughness is almost 3 times larger than PDMS. So this is exactly the reason we are really saying, why not use this super molecule as a substrate for trap film fabrication? So in this case, what do we do here? Okay, so I can show the screen. So this is actually, we cut it purposely, then stretch, the crack will not migrate. So this is how we fabricate this kind of anti-tearing electrodes, very efficient and approach method. And then because this, then we can use for this kind of animal experiment. You can see we can really embed our electrode for this kind of EMG, muscle activity monitoring. And this is the fresh mouse. You can see the wound here. And after 1 month, for same mouse, still life. It's kind of long-term stability of electrodes. It's not toxic. And also we can really continually get this kind of muscle activity there. So this is the way how we fabricate these stretchable anti-tearing electrodes. And then potentially can be used for muscle activity monitoring. And then this is the mouse. Now we are working on this kind of human trial to try this electrode can be for long-term implementation. Of course, not only kind of continuable film, if you use kind of mask, you also can fabricate this kind of stretchable arrays. This is also very useful for this kind of based on this kind of trap approach. Okay, so this is something about just talk about stretchability, but of course we also handling with other kind of issues about biocompatibility, reliability, and durability. I will not mention too much here. Give you a few quick examples, not too much detail. First one, for example, use this kind of cell protein. We lower down the S modules from gigapascal to megapascal, even go to kilopascal. So this is a way to increase this kind of stretchability, and also use our trap approach to make this kind of conductive electrodes based on this kind of silk. And then also we try to use this kind of electrode spinning to make this kind of porous electrodes based on this kind of silk. Make sure when electrode fabricates, there's still also a lot of porous allow you to gas in, gas out. So take a strict example here. This is our silk-based electrodes. This is gold without porous structure. This is the medical electrodes. After exercise, you can see our electrodes still have a good temperature. It's like a skin, but another 2 electrodes accumulate heat because they don't have gas in, gas out. So this is something, especially in Singapore, under sweaty condition, can be a huge problem for this kind of outside door exercise. Another example is about electrode stability issue. You can see for exercise tremor tests very often used, especially for this kind of continually monitoring your heart status. But we know already you need to have 10 electrodes adhere on these different positions. And then we will go for this kind of long-term exercise tremor test. The nurse always give you this kind of tap to ensure electrode will not peel off, because under the sweaty condition, electrode is easy to peel off because sweat problem. The reason here is because adhesion stretching issue. With more humidity, the adhesion will significantly decrease. So this is the reason for electrodes. And how do we make sure this have these electrodes adhesive under sweaty skin? The answer is yes. We use our trap approach kind of concept, and also here use a polymer, semiconductor polymer with this kind of silk-based electrodes. For our electrodes, good point is under high humid condition, the electrodes still have high adhesive. Higher humidity, high adhesive. So this is like these electrodes. Tap on this kind of wet skin, it's very adhesive. It can catch almost 100 grams. This material, this kind of stuff. It's kind of very adhesive material. So in this case, this electrode can be used for this long-term ECG monitoring, for continuous monitoring under sweaty conditions. Okay, so this is some exactly our student to running under this kind of treadmill for this kind of long-term monitoring. Okay. And not only about on skin, now also can underwater. We also can do it. But of course, if people interested, you can go this paper for more reference. So this is under for aquatic ECG monitoring. This kind of waterproof electrodes. Okay, basically, for previous parts, I more tell you about from materials angle, how we fabricate this kind of conformable bioelectronic interfaces. If interesting, you can read our other papers as well. Now, second part, I will tell you how important for digitalized biological perception or in the following for action. Perception means you can really sense and convert to this kind of brain for this kind of more full action following up. Okay, I think maybe most of people read this paper 2 weeks ago, just 2 weeks old in Nature. So this is a very, very interesting development. This is for one paralyzed man, 65 years old. And then he cannot control his hand for writing. Which this is kind of Utah array. Okay, embed in your brain. Then the people can really transfer his intention by this kind of machine with this kind of AI and into his hand to writing. So this is the way to solve this problem, mind over matter to writing. Okay, and people can, this 65 years old man can write almost 90 characters now per second by this kind of brain chips now. And then for this kind of development, I would say it's not only for this kind of paralyzed man and all the other kind of people like a stroke, patients also very useful. Now the question is very important for this kind of like interface part. This is Utah array. Yeah, it's very useful, but unfortunately, not many people like it because it's still rigid. And as just earlier mentioned already, for Utah, for the human brain, it's very soft, like tofu. So this is something very, very challenging for this kind of implantable experiment. And then for skin experiment, similar. For skin, our ideally impedance of human skin is about 10 kilo ohm. So it means if your impedance of electrodes lower than 10 kilo ohm, then you don't have this kind of interface impedance issue. But unfortunately, this is all the kind of different kind of dry electrodes or wet electrodes. In terms of impedance, it's always high, more than even 1 magnitude or 1 magnitude or 2 magnitude higher. As a result, the signal noise is very low. And then sometimes the low signal you cannot pick up. Okay, so this is something one very challenging for this kind of human machine interface experiment. It's also brain machine interface, also similar problem. And then we do one work in here is based on this kind of alginate polyacrylamide. So for this kind of polymers, we buy our suitable tune. We can significantly reduce the gap between electrodes with the skin. You can see typical commercial electrodes is always gap here. So this is our peak. This is the peak skin. This is electrodes, a lot of gap here. But here, this is less gap, or even almost you cannot see it. As a result, you can see the impedance much, much lower. And then, of course, in terms of adhesiveness, the red color here is our samples. It's also very adhesive. So this is something we here called compliant ionic adhesive electrodes with very low this kind of bioelectronic impedance. So in this case, we put this kind of electrodes on the skin to get a muscle activity. There are two advantages here. First one, increase signal noise ratio. The second one can significantly reduce the crosstalk here. And then one of kind of information I will share here is kind of the maximum voluntary contraction. So this is very important to measure in terms of this kind of contraction of this kind of muscle. You can see for our electrodes, we can under very low kind of contraction, we still can get signals compared with the commercial other electrodes. So this is our advantage. As a result, we can significantly reduce the size of the samples and also avoid the crosstalk. So this is the way we can do it. You can see for this black one. We just use very small, and also have can really reduce the crosstalk. Okay, because most of the case for commercial one, you will lose the signal in between. But for our electrodes, still a lot of this kind of muscle activity. This is very important for this kind of human machine experiment. Like this example, this is a commercial electrodes. I have connect the muscle with the robotic hands already. Now we have this kind of, you can see, I can repeat again. Anyway, so you can see a lot of this kind of electron here. So this is the way to get muscle activity. And then to link with the rubber hands. Now the subject here grabs the needle, immediately the muscle have activity, and then I can transmit to the kind of rubber hands for fold actions. But for this commercial electrodes, you can see the man grabs the needles, but the rubber hands no response at all because the signal is too low, and also they are crosstalk properly. And then use our electrodes much smaller size, only about 10 millimeters square, and then also very kind of very sensitive. You can see now grabs the hand, the finger length, and also the rubber can also immediate response. So this is the way you kind of mind. You forget about the middle part. Now this kind of human hands is more mind control of rubber hands. You can do it already as long as you have a signal there. So this is something we feel is important. Have such kind of sense digitalization parts. So now this is more about beginning and status. And also now we also have a time resolution. Beginning just a muscle activity, but now we also can go to this kind of time resolution. It means also strength, how tight you can do, and also how fast you can do. So this is saying tight with fast. Have two kind of parameters we can tune. So this is because this kind of excitation, contraction signal of this kind of muscle there. How we do it? So we develop this so-called locally coupled electromagnetic interface. So it's kind of electro skin here, but this skin have two functions. One function is the stream, electro skin is the stream function. The second one is electro can monitor this kind of muscle activity. There are two kind of functions there. So you see, our electrodes have much higher kind of signal compared to commercial electrodes, and also have this kind of strain response. So as a result, now we can distinguish four types of this kind of activity: tight or less tight, fast and soft, and less fast. So this in the end have four kind of figures. You can do it. Okay, and I'll give examples how it look like. Okay, you can see this is the same times for four screen, but four screen indicate this is the right side tight and fast. So this is less tight but fast. These two are slow. This is tight. This is less tight. You can see for the spectrum here. You can see there's significant difference already. So this is the way we can really for this kind of grips like a human. Okay. So this is the way how it can do it, control interface between a human with the robot with the machine. You can see. Okay. So this is kind of for comparative experiment to do it. Okay. So not only for this kind of human machine electronics interface parts, and this also can move forward as this kind of device put on this kind of variable device parts. And what we do is this is something really can get high quality data of the human for healthcare monitoring. And one example, 2 years ago, we worked with Zhenan together to make this kind of stretchable passive tags. This can be used for wireless body area network monitoring. So by this moving, this is all our wireless kind of without and also powering, and then can for this kind of continuously for 6 different kind of healthcare sensing nodes, include pulse, respiration, and also body movement simultaneously. So this is something still a lot of work ongoing now. And then in terms of digitalization, not only for human, in fact for nature, like a plant, also this kind of electrical signal response. Okay, see, this is something one very often if you plant, once this conflict, external stimuli, whatever temperature or mechanical strength, chemical strength, and so on, you always have this kind of electrical signal response in plants. So this is something well known for plant electrophysiology. And in this field, people typically use this kind of electrodes, silver wire electrodes. This is something one invasive and also easy to destroy the plants. Low signal quality is not very good. And also because the plants have different kind of structure, could be vexed, could be hairy, rough, and also fragile. So that's why we did this kind of conformal electrodes for plant monitoring. So what we developed using this conformal gel. So this is kind of ionically conductive materials that can transform from solution state to the solid state under room temperature. This is sold by this model. Okay. But this model just show you the room temperature and very cold temperature kind of liquid. Room temperature becomes gel. So in this case, you put on this kind of heavy leaf structure, immediately become this kind of gel-like materials. And this is our electro material, thermal gel materials. So based on polycarbonate, you can see electrodes is very conformal. Although structure is very conformal, compared with other kind of electrodes. Okay, so this is something a lot of this kind of crack on top. So this is something good for this kind of thermal gel electrodes we can have compared with other kind of hydrogel materials. Have very good this kind of signal there. Okay, then in this case, we can use for this kind of thermal gel for this kind of plant monitoring. You see, so here. So this is something one we can put on top. Have two experiments here. White is our electrodes, thermal gel electrodes, and red color is other white electrodes. You can see the red color, the signal is change a lot, but for white one, it's pretty stable in the case. Whatever how stable, noisy, the signal still is good for this kind of electrical readout. And the even worse is here we apply this our chemical stress or mechanical stress. We can get this kind of electrical signal of kind of from the plant. Here we burn it. You can see the burn immediately trigger this kind of electrical response. You can see immediately this kind of response there. So this is something that I would say very useful for electrodes for this kind of plant healthcare monitoring, and also other kind of sensor we are working on. And then of course, I just mentioned already, you need action, right? Whether this kind of electrodes not only monitoring, can also trick this kind of action. The answer is yes. Here we use the fry trap. So this fry trap is kind of well-known plants. Okay, it's sensitive for mechanical mismatch, the mechanical touch. For the fry trap, you get touched two times, then the fry trap closes. So this is something well-known. So what we do is we put these electrodes, conformal electrodes, on this kind of skin. Have two electrodes here, and then this electrode can, because not only monitoring, can also electrostimulate to close the trap, as here. Why we can do it? Because in mechanical touch, once you touch two times, immediately they have this kind of the potential generation, action potential. Because this action potential, they will close the trap. In a similar case, when you apply two times this kind of electrical signals, they also can lead in this kind of trap close. So this is the way electro stimulate to control fry trap close. And also we can read understanding in which voltage you need. You need about 1.5 watt to close this kind of trap. 1.5 watt. In this case, is useful. So once I understand this one already, then we can connect with Wi-Fi. Okay, so this is so here. So this. You can see. We can control the Wi-Fi on, off. You see, immediately this I can click again. On to watch it stimulate, immediately close this kind of trap. So this is the way how we can use this kind of electrically outside source to control fry trap. Okay. And not only here, but this also can do it because we can control the timing. We can control this kind of action to really grip this kind of pick up this kind of sim wire. And also we can use this one to control, to capture a moving object, because we know that when object reach there, we can really control the time to close and the captures. So this is potentially for this kind of biorobotics can be useful. But big problem for this one is what? You cannot return so fast. Can easily close, the open will take hours. This is something about, I would say, the problem at this moment. But I would say in generally, in terms of the plant one, I would say it's a very emerging field. here we always call Internet plants. If we can use this kind of conformal electrodes, we can really connect implants in a cyber chemical physical space. Then this potentially can build plant networks, can build plant sensors, and also good for this kind of precision agriculture. Okay, so this is something I would say is really useful potential. The last part, I will take maybe about another 5 to 10 minutes to share you how you, based on this one, know our know-how and come up with the AI together to extend our human sense. So in more simple way, I would say convergence of matter and the mind. In a way, physical and digital technology put together. So this is something what I would say potentially will be useful and then can extend our human sense. So take example for human brain. So human brain is very kind of interesting in this kind of processor system. And then take example here, when we have this kind of vision, what I see it. And also this is some somatary sensor here, what the action here. Once the two all in one together, you will transfer signal to this kind of primary association area. And then for further go to this association area and laterally immerse or fuse in this so-called multi-sensor neural areas for signal processing. For visually also send primary association area, and here's this kind of multi-sensor neural fusion. And then as this together can generate feedback for further action. So this is something called sensory processing hierarchy. We know already we can fabricate this kind of strength sensors. We can have a lot of this kind of optical sensors. But how we link together? So exactly we learn from here, multi-mode fusion. And here we involve this kind of machine learning, using AI together to this kind of machine learning. So what do we develop this so-called bio-inspired somatary vision associated learning framework, 2-in-1. In this part, we use a convolutionary this kind of layer network, CNN, for this kind of picture analyzing. We have another one called sensory information, strength information, put together. So here it's called fully connect neural network. But because a lot of cases we have less data, so that's why here where we come out another one so-called sparsely connect neural network, put together to this kind of processing and then to classification. So this is the whole framework we developed. So exactly this is how each sample we have. For each hand gesture, we have one kind of optical picture. We also have 5 somatary sensor information. We put 5 strength sensors on here. So this is kind of one information for one picture. And then here we have 3,000 samples. Now you know how challenging for our students to build this kind of 3,000 data. So once it's 3,000 data already, then we can do the machine learning, as we just now saw already, and then do the classification, have a precise kind of recognition. At the end, find the best kind of accuracy is use our association framework we just now saw it. It's very accurate. Under different priorities, still very accurate. So this is the way how we can have a 10 hand gestures, we can get it. In this case, this one, we can use hand gesture to control machine. Okay, so here, take example, because this is our model, almost accurate under this kind of 100%. So once you can do it, then you can really precisely use this kind of hand gesture to control the robotics. Okay, this is something like one under this kind of multi-mode fusion approaches. So this data is no association now. Okay, so this case you can see sometimes you can have some error somewhere. You can not really recognize there's some kind of error there. But if you use our BSV mode, it's almost 100%. Okay, under this kind of normal kind of conditions. But of course, under this kind of bad conditions, the accuracy will be a bit less, but still very good in this kind of human machine control parts. So this is the way our idea is how we can extend human sense. Okay, another part is the way we connect this one with our e-nodes. Because we know already in human how we can distinguish the odor. In the nature, we almost 1 trillion different kind of odors, but human only have 400 receptors, about 400 receptors. How 400 receptors can really recognize the 1 trillion odors? Because this kind of combination. So instead from here, we derive here so-called deep calorimetric barcode. So barcode here mimic this kind of receptors, and here we use the CNN, convolutional neural network, to mimic this kind of brain. And then we can, of course, you do a lot of this kind of classification early, quantify based on this kind of color change. Then we can really use for this kind of distinguish the food freshness, especially for the meat. How you match the food in terms of meat is fresh or not fresh or spoiled. This is just based on reading out. You can do it, but of course you can read more information in these papers. Okay, finally I'll give a short summary. So the skin, just now I mentioned, is kind of interface to transduce the biological sense into digital signals. We start from biotronics parts, how we develop this kind of interface, and to get this kind of sense digitalization. Last one, come up with AI for further perception and also extend human sense. And then I would say this is still ongoing for skin. It's kind of emerging field. You can see you need to involve not only material science, electrical engineering, mechanical engineering, biomedical engineering, even data science. Personally, I'm looking very optimized for this direction because it's really kind of make impact, not only from manufacturing, healthcare, social robotics, even human augmentations. I do believe if you sense the world, you will pursue the future, you will create an endless possibility by the e-skin. But I always want to highlight again, this is a very kind of interdisciplinary field. You need a lot of people work together. And also now it's time for research innovation and this entanglement age. For me, I'm really open for collaboration. If anything you want to work together, email me. I'm very open to on this one. It's a very good opportunity now. Finally, thanks for my students for the hard work. And also thanks for funding agency for the strong in-kind support. They believe us and we do our best. And also thank our collaborators. Finally, thanks for attention. Stay healthy, stay connected. I'm happy to take any questions you have. Okay.
All right. Thank you for your wonderful talk, Professor Chen. Now I would like to hand over to the Q&A session. So we will begin with the interviewing question first, and then we will open for the guest to ask the question. Let's begin with the first question from GSC MSE. What will be the end goal for the stretchable electrodes, such as maybe stable up to 150% strain?
Oh yeah, now, this is something I would say depend on the field applications. Okay, for on skin, if you just for the electron on skin, and skin is about 70% stretchability. So this is good enough already. If you can make about 100% stretchability, it's good enough. But however, for in a implant experiment, like this kind of a lot kind of other experiment, like bread experiment. For a bread experiment, you need almost 250% stretchability. So that's why it's really based on what you need. It's not the one I just fabricated 200% or 100% stretchability. It's really based on what you need.
All right, it depends on the application.
Yeah.
So the second question would be, given the situation right now, it's on the pandemic situation, will such sensor be possible to be manufactured on the large scale for commercialization to monitor patient health without the need for complex equipment?
Yeah, the answer definitely yes. In fact, if you read the paper from John Rogers' group, you have developing few systems on trial now, for human monitoring. And also, my group also work with the A-Star team. We come out with kind of sensors lab on mask. So we put the sensor on mask for this kind of temperature, for skin temperature, and also for heartbeats, and also for oxygen saturation level. We can do this kind of continuous monitoring. But you need to go back. One question is, now the limitation is about manufacturing. Okay, because all of based on this kind of flexible capability, kind of fabrication, not typical CMOS fabrication protocols. So this is something I would say the challenge now. So what I'm doing now in NTU, I try to build this kind of capability. We are building one experiment lab now. We want to, in this year, we can really have larger scale soft electrofabrication. So once this can be done, I would say it's really potentially a lot of application. The second part, I would say, if we go for commercialization, important part, I would say, industry acceptance. Because industry, you want to commercialize one product, make sure it's very stable, and also repeatable, reliable. But unfortunately, use our current approach, you don't have this kind of standard monitoring. No way you can go to this kind of commercial. So that's why a lot of research, we always stuck about TRL3. And then for industry, they will look at TRL6. So 3 and 6 is very big gap there. And then I would say this is something one, my group is trying to bridge this gap now.
I see. Okay, so the next question will be from Li Yun. She asking about the electronic sensor. How does the concentration of nanoparticles embedded in a gel affect the sensibility of the sensor?
Well, this is, because I don't know which one should refer. I would say it's really depend on the application parts. Because a lot of cases, in the flexible electronic area, electric sensor parts, we always under this kind of trade-off. Trade-off means a lot of cases you want to have very good connectivity, but stretchability is very bad. And then sometimes also adhesive is also very bad. So that's why we have to balance the conductivity, sensitivity, and also adhesive, and also other kind of performance parameter there. So that's why you don't have one particular formulation. It's you need go for a particular case to study. So that's why flexible electronics parts, I would say, more now is engineering. It's engineering. It's not much about, they do have science, but more engineering problem now.
So does that mean that it's better to separate the property of each, like materials for the device? Let's say if you want to achieve adhesiveness and if you want to achieve stretchability, we need to separate the material, isn't it? Your question, your answer.
Yeah, you need a sacrifice, not separate. Sacrifice.
Yeah. Okay, so it brings to the next question from Li Yun. She asked about how did you control the amount of nanoparticle that penetrate to the gel? Is it by Joule heating parameters?
Oh yeah, but yeah, can be by Joule heating parameters, and also can really control amount of the particle you deposit.
Okay, so the last question would be from me. I would like to ask about the electronic skin device. What would be the bottleneck for this kind of device? Yeah.
I think for this field, the bottleneck is people. Yeah, why I say the people, because you can just now see a lot of example now. Our research is not typical material science. We start from material science. You can see we have a lot of so-called new, in a lot of this kind of fields not within material science. And then for students, I would say it's very challenging. My students, I do admit, working very, very hard. And then, every day they're learning something new knowledge or new kind of information, new kind of capability we don't know before. Because this is something one kind of interdisciplinary field. So that's why I would say the bottleneck, the problem is really human. It's the people. You really want to do it. You want to learn more new stuff. Then it really can make happen. And then also now say what's the people? Because in academic parts, we understand for students, they more care about publications. But you know, in this field, sometimes publication is not so easy because you need to learn so many and then get published. Sometimes also not published, not so easy, and not so high quality papers. So that's sometimes, you know, demotivate our students. So that's something I would say, how, you know, we translate or train our students to believe this is a very field deserve to spend time. I would say it's also very challenging. The third challenge I mentioned about human is about from industry side. Because for industry, they always assume, oh, you have so many breakthroughs. Now it's easily can translate and put our industrial fabricate. The answer is also no, right? I mean, because this is still need more kind of test, need more this kind of timing to invest, understanding. So this is something one human problem, and not a barrier between this disciplinary.
All right, thank you, Professor Chen. Next, I will hand over to Vijay and Aditi for the Q&A session. Vijay, Aditi, please.
Hi, thank you, Prof Chen, and thank you, Heritai. So I'll start by asking a few questions from EEE GSE. The first question being, can the electronic skin be used as smart bandage? By smart, I mean that can it adjust its features according to the skin wound? Example, changes in temperature and pressure.
Yeah, I think maybe yes. You know, we don't have this kind of research experience, but I would say simple answer yes. But you know, you have to make it work, right?
Thank you. Another question is, what is the power source for this e-skin, and how does the wireless charging work?
Oh yeah, now for this one, so it's still, you know, at this moment you use the I cannot remember antenna. I think I cannot remember the approach name, but I think that based on this kind of antenna, it's a well understanding one. Yeah, wireless power transmission.
Okay. Is there any
Not new for that part.
Is there any scope for the solar-powered electronic skin as well?
They do have people work on this one. Yeah, not for us. Yeah, people really, you know, try to see how solar can really connect with the e-skin device part.
Okay. We also have a few questions from Vivek. He wants to know, could you please share how e-skins can be potentially used for brain-computer interface applications?
Oh yeah, in fact, this is a lot of working now for brain interface parts. And then now, you know, the typical brain interface for typical neuron scientists use the Utah array. But Utah array is kind of silicon-based, this kind of chip. It's very rigid. So that's why, you know, a lot of researchers try to use kind of soft conformal e-skin electrodes on the brain. And then they do have many preliminary work, but I would say still more work to be done. Even for our group also working on this one. But at this moment, I think more challenges how we ensure the stable transmission, the single stroke transmission. It's not just get a one-time signal. How you implant like get transition, get a continuous kind of signal. This is something I would say very, very challenging because you know, once you have this kind of electrodes, you put this kind of human and brain, immediately have wounding there. So wounding immediately generate a lot of this kind of impedance. So this is something a problem now. So that's why people now looking for biocompatible e-skin. So this is people are doing now. Yeah.
Okay. Another question by Vivek is that recent works by Neuralink or even previous work using Utah MEA has demonstrated that deep brain electrodes BMI are more accurate and could be safer. Could an e-skin solution ensure high accuracy BMI with high SNR, considering it might be only on the surface cortex of the brain?
Trade-off, I would say, I only can say trade-off. You don't have an all the best solution now. Even for e-skin, currently still in the early stage in the BMI, the brain machine interface parts. So that's why I think I cannot comment too much at this moment. I would say still more the people like from neuron biology, from the electrical engineering, from material science come together, even for data science together. I would say, yeah, I cannot comment on many because at this moment, skin didn't show a significant advancement compared with the current Utah array.
Okay. Recently, there have been some very interesting works related to neuromorphic tactile sensors, such as new touch from NUS. Could we see this neuromorphic sensors being more widely accepted for robotics applications in the future?
Yeah, they do emerge on this direction, but I would say, still too early to justify. Yeah, you have to, you do see something new perspective.
Thank you, Prof. And now I will take questions from the Q&A tab from the audience. So the first question that we have is from Norazin. So the question is, can this technology be a wearable tool like Fitbit, but without removal, like wearing a watch? Is it worn on our skin like a patch for monitoring of our basic vital statistics, example, heart rate, number of steps, calories burned, and how can the material last to withstand the daily activities, example, sweat or showers?
Yeah, I mean, yeah, definitely. This is something else, a list of questions to be addressed by each scheme, because so far, for take one example, material stability issue, right? Because our use is always soft material based. If for one-time usage, it's okay, but for continuous monitoring, will be challenges. So that's why we are trying to use the so-called hybrid approach. It means a lot of sensor parts still based on CMOS parts, but interface parts can be based on e-skin electrodes. So I would say a lot of research still ongoing on. And then the big challenge is kind of human. We need more people in the field because I only have two hands. I cannot solve all problems. And then if really more people can jump in together, I would say it's really a lot of things we can work and we can solve down.
Thank you, Prof. Next question is from Parvati. How viable is the 3D printing flexible electronic skin?
I didn't hear. Can you repeat again?
How viable is a 3D printing flexible electronic skin?
Well, it's really, you do 3D printing, right? You can print everything, right? I would say important part was what the questions you solve. Yeah, I would say based on question.
Okay. The next question is from Xiaodong. They ask that for the thermal gel to detect electrical signals from plant, how are the electrodes removed? Is it via applying a cold surface? Is it easy to cleanly remove the thermogel from the plant?
For plants, the electrode we don't repeat use electrode because at this moment it's the fundamental research part, and then we just use and then remove it away. And then I would say still in early stage at this moment. Yeah.
The next question is from Yujia Tian. They ask, may I ask what's the thickness of the gold film? What do you think is the potential for piezoelectric monolayer materials?
It's about 100 nanometers, 100 nanometers thickness.
Okay. The next question is from Minu Nair. Is it possible to integrate electrodes into piezoelectric stretchable polymer substrates? Is trap method viable for such substrates?
Yeah, it's possible.
Okay. Thank you, Prof. I guess these are the only questions from the audience for now. If you have any more questions, kindly post it in the Q&A session, Q&A tab. We do have one question from Arturo. He posted in the chat. His question is, apart from the mechanical advantages of e-skin, does your superficial electrodes give any advantage in reading deep muscle signals in terms of selectivity? For example, identifying the activity of deep muscles in the human forearm?
Yeah, I would say at this moment too early to justify on this one. I cannot really comment too much because this is something you need more experiment to confirm. Because I would say that in terms of mechanical parts, it's not easy already. And then definitely, it's whether can go for deep muscle signals. At this moment, it's too early to justify. The only thing we know is we can really get kind of low signal now.
Okay, thank you, Prof Chen, for the incredible talk on the electronic skin. Now I would like to ask Rajesh to take over for the closing remarks.
Thank you, Aditi. Thank you, Prof Chen, for giving us a very wonderful insight on the talk of electronic skin. And thank you to everyone for spending their Friday morning with us today. So before we conclude our session, I would like everyone to share their feedback on the webinar by scanning the QR code, which will be shown on the screen anytime soon. The attendees seeking seminar endorsement are required to submit the feedback form. So Chris, is the PPT ready? Thank you for watching and have a great weekend. Stay healthy and be safe. Thank you all.